Today, we're going to cover Chapter 11, Distributed and Decentralized Optimization. Distributed optimization uses a set of computers connected in a network to solve an optimization problem. Those computers in the network are called agents. The motivation is when an algorithm running on one computer does not meet the required performance, for example, causing out-of-memory error or simply taking too long to finish, one can either improve the hardware by upgrading the CPU or memory and run the same algorithm, or use more computers and decompose the problem into subproblems and then run a distributed optimization algorithm. Approach 1 is often less cost-effective and may never reach the required performance because the cost of purchasing the hardware can increase exponentially as the hardware reaches the physical limitation, and the physical limitation may prevent you from reaching the required performance. Therefore, cost of 2 is often the more favorable and sometimes the only choice. However, approach 2 requires us to decompose a problem and study new distributed optimization algorithm, which we cover in this lecture. The title of this lecture includes both distributed and decentralized, the two words. However, we're going to first distinguish between distributed methods and decentralized methods. Distributed methods perform computation over a network. In other words, the problems and their data are distributed over the network. It's a broader class. Decentralized method is a subclass because they do so without a central node or central coordination. Roughly speaking, when communication latency and bandwidth cost much more than computation, decentralized methods have an edge because they don't need a central controller, which is often the communication bottleneck. This means there are some application examples where decentralized methods are often preferred. In drone fleet control and other real-time decision applications based on agents' local sensor data, decisions have to be made really quick. Therefore, long-distance communication or high-latency communication are not preferred. So in this case, decentralized methods can be the only choice. Also in wireless sensor network, since the communication is done by wirelessly, and wireless communication tends to have a longer latency, and it's very difficult to do long distance wireless communication. Therefore, a center will have a disadvantage. In this case, decentralized methods are also preferred. To be concrete, in this lecture, we're going to solve a finite sum optimization problem where all the Fi's are CCP and approximable, and all the HI's are CCP and differentiable. The setup is there are n agents, 1 through n, and each of the agents performs its local computation because it has its own Fi and Hi functions. It also communicates over a network, and they work together to find the shared solution X star. Chapter 11 of the textbook also considers the more general formulation which allows an extra CCP and approximable function R as the common regularizer. We're going to look at both distributed optimization with a central node, as well as decentralized optimization methods without a central node. Let's first look at distributed optimization based on centralized consensus. Consider a parameter server network model where there's a centralized agent, which we call parameter server, and n individual agents. We use the word parameter because this setup is often used in distributed optimization for training machine learning models, and the training is going to decide the parameters of the model. And those parameters are often stored and updated by the server. And we study distributed optimization methods based on the consensus technique. Let's introduce the technique. First, consider the simplified finite sum problem where there's no function f, only functions hi. And introduce the consensus set, which is a n-tuple where x1 equal to x2 and equal to xn. And using this consensus set, we can reformulate the above finite sum problem of one variable into a problem with a finite sum where every hi has its own individual variable xi, and all these xi together lie in the set C. In other words, all of them must equal one another. They're clearly equivalent. In the reformulated problem, the objective is smooth, and the constraint is easy to project onto. Therefore, we can apply forward-backward splitting, or in this case, gradient projection iteration. The first step is to apply gradient. Since we have separable objectives, gradient amounts to apply gradient descent to every component xi. And then we project x1 through xn k to the half to the set, to this consensus set, which gives us the average. We can also eliminate these xi k to the half by plugging the first iteration to the second iteration, and then taking the average of xk will give you xk. So after the plugging, after the substitution, it amounts to taking the average of the individual gradients. So we take the average of the individual gradients and call it g bar k, and then subtract this average gradient with step size alpha from xk. And this is what we call distributed gradient method. Applying the analysis of FBS, we get this. Assume a solution exists. H1 through Hn are all LH smooth. Take the step size no more than 2 over LH. Then the iterates will converge to a solution X star. When the functions H1 through Hn are not differentiable, we can use subgradient method. And in that case, this method is called distributed subgradient method. Let's examine this method and make sure the so-called distributed gradient method is indeed distributed. In particular, we can let agent I independently computes gradient of hi of xk. Now for this step, the gradient needs information xk from a parameter server, but can compute this gradient independently of other agents. And then all the agents coordinate to compute g bar k, which is a reduce operation. And for example, they can send their individual gradients to the parameter server and let the parameter server take the average. Then the parameter server will compute the gradient descent step, and after that broadcasts xk plus 1 to all the individual gradients for them to start their next iteration's computation. Now let's study distributed ADMM. Now consider minimizing sum of fi. We omit hi for simplicity, but if you include hi, you can get distributed linearized ADMM. Now using a slightly different consensus technique, and this time we also introduce an additional variable y and let every xi equal to y. And we can refit this formulation into the typical ADMM form. So we're using matrices, block matrices. We write the constraints xi equal to y for every I into this form. So it's clear that we have a matrix times the stacked x variable and another matrix multiplied by y with objective function from the x side. Again, the objective functions are separable in xi, and when y is fixed, only consider this part. All the xi's are separable because this is a block diagonal matrix. So we can apply the ADMM method. Apply ADMM, the standard ADMM. You obtain this three-step method. You update the first primal variable x, then the second primal variable y, and then update the Lagrange multipliers. Because all the xi's are independent, are independent in constraints and in objective when y is fixed. Therefore, individual agents can update their own xi's. And to update y, because y is connected to all the xi's, you work out details, and also because y has no individual objective, the y update has a simple averaging form. And then you have to update individual Lagrange multipliers, ui's. You can simplify the iteration by noting that after the initial iteration, the mean of u1k through unk is 0. So in other words, this averaging operation applied to uik's going to give you 0. So therefore, instead of using y, we can simply use x bar to represent the mean. And using x bar, we can combining terms and simplify these three-step iteration into 2 steps. Or the first step, you have to calculate the mean and then take the proximal with respect to every individual xi to get the update of individual xi k plus 1. And then in the second step, you have to take the mean and update the individual ui k plus 1. In the next iteration, this mean is already computed, and then for the next iterations, you won't have to compute the mean again. This is called the distributed ADMM with a centralized agent. Because this is the application of standard ADMM to convex problems, the convergence follows from the convergence of standard ADMM. Let's verify this distributed ADMM method is indeed distributed. So we can let every agent independently performs the xi and ui updates, provided that they already have the mean. And after the agents computed their new xi's, they need to send their information, or they need to somehow coordinate to get the mean of all the xi's, denoted as x bar, either with a central agent or using network reduction technique. Remember, ADMM and DRS, Dalash-Radford splitting, are equivalent in multiple ways. So check out exercise 11.7. You can obtain the same distributed ADMM method by applying Dalash-Radford splitting to the equivalent problem, where we use the first consensus technique by introducing this constraint set C. Next, we introduce a distributed method obtained by applying the primal decomposition technique. So consider this problem where there are n variables and one special variable z, and z is called a coupling variable because it's inside every single objective function. The total objective is the average of the single objective functions. So obviously, once optimal z is obtained, we can then obtain optimal xi. However, the choice of xi certainly affects the choice of z. So we introduce, for every fixed z, we introduce the infimum of fi over xi, and we call the infimum phi, which is a function of z. Therefore, the problem is really equivalent to minimizing the sum or average of phi's of z. Clearly, if all the phi's are differentiable, we can apply distributed gradient descent, where we calculate the gradient. There should be an equal sign, and then taking the average of the gradient multiplied by step size alpha and subtracted from zk, the main iterates. But often, in many applications, these phi's are not smooth, they're not differentiable. See exercise 11.2 for how to compute subgradients of phi1 through phi(n). When they're not differentiable, we're going to obtain a distributed subgradient method. The next, we're going to obtain a distributed method by applying the dual decomposition technique. Consider the equivalent problem where we have duplicated variable z to z1 through zn and ask all of them to equal to an additional variable, common variable y. And then we assign Lagrange multipliers vi's to them and write down the Lagrange. From the Lagrange, we can write down the dual problem. In the dual problem, we can eliminate the primal variable y, and for the primal variables xi's and zi's, we can write them down. We can include them in the computation of Fenchel dual or convex conjugate and calculate the convex conjugate fi star, where the first variable is 0, and the second variable is a dual variable vi. And we define this function as function psi I of dual variable vi. And the dual problem reduces to maximizing or minimizing the mean of psi I vi subject to the sum of vi is equal to 0. So this is different from what we saw before. Before we had problems where the individual entries must equal one another, but here we have a different but still simple constraint where all the components sum up to 0. So this is also a constraint that's easy to project onto. When psi i's are differentiable, we can apply projected gradient descent, and this gives us a distributed algorithm. We let every agent compute the gradient of psi I. This should be equal sign, and then project these gradients onto this sum to 0 constraint, which is going to give you this form where g bar k is the average of g1k through gnk. When psi's are not differentiable, then we need to calculate their subgradients, and they're given, this calculation is given in exercise 11.3. And in that case, we're going to get a distributed projected subgradient method. Next, we're going to introduce some decentralized optimization methods where instead of centralized consensus, we're going to use consensus through a graph, or we call graph consensus. We make a comment on the word graph. Graph has two distinct meanings in mathematics. The first meaning is very common. Say we plot the graph of a function on a graphing calculator. It describes the relationship between the input and output of a function. We can also define the graph of an operator, which is written as graph A, where A is the operator of concern. And in a later chapter, we're going to introduce scaled relative graph, which we can use to prove and analyze lots of algorithms in this book. However, in this lecture, we're going to use the second meaning of graph. It is a concept in discrete mathematics to represent networks. So network is more physical, graph is more mathematical. Given a network, let's define a graph. A graph consists of a set of vertices and a set of edges. A vertex is also called a node. An edge is sometimes also called an arc. And in this chapter, we're going to assume that the network is finite. Therefore, the graph will have nodes 1 through n. Assume the graph is undirected. Therefore, whenever there's an edge I to j, there's also an edge j back to I. So it is an unordered pair of distinct nodes I and j. Assume the graph has no self-loop, so I to I is not an edge. We also assume this whole graph is connected. That is, from any node I, there's a sequence of edges that connect I to j. is a sequence of consecutive edges. We need graphs to represent a network without a central coordinating agent. Here's an example. We have 6 agents, and their connections are represented by these solid arcs. So the set of V is 1 through 6, and the set of edges are these pairs. For example, 3, 4 means this connection. Here, an agent or node represents a computational agent that stores a part of data and performs a part of the computation using its own data. An edge ij represents a direct communication link between I and j. So I and j can directly communicate. We need a little more notation. If ij is an edge, then we say j is adjacent to I, or that j is neighbor of I. And for every agent I, the set of neighboring nodes is written as n sub I. And the cardinality of n sub I is certainly the number of neighbors of I. And because there's no self loop, this does not include the node I self. Using the notation of graph, we can reformulate problem 1 into this form. We have introduced xi for every individual fi and hi, so the objective becomes separable. And the summation is no longer 1 through n, it's over I in V, it's the same thing. And instead of using a standard consensus technique, we just let xi equal to xj for every edge, for every pair of nodes that are directly connected. And because the network is a connected network, so every node has a sequential set of edges connecting all the other nodes. So this actually means, this set of constraints actually mean all the xi's, all the nodes have to equal one another. Let's come back to this topic again, compare the centralized optimization to standard distributed optimization. Because the network is connected, all agents can communicate with one another. If 2 agents are not immediate neighbors, they can use other agents in the middle to relay information. So any optimization method, even if the method requires a central node, can be executed over a network through relayed communication over multiple edges. However, in distributed optimization, communication tends to be at least an order of magnitude slower than computation. So communication tends to be the bottleneck. So we consider algorithms that communicate across single edges without relaying information and making long distance communication, and also without creating a bottleneck by communicating with a single central node. So not dedicating any agent in the graph as a central node also improves the reliability of this algorithm against the failure of a single agent or the failure of some critical links. Also, because information is only directly sent to your neighbors and there's no central node, to some extent, this algorithm also helps protect the data privacy of individual agents. The first decentralized algorithm we study is decentralized ADMM. Like before, there's always a bit of reformulation going on so that we get a method that can be fit into the ADMM form. Then we can apply ADMM. For simplicity, assume these smooth functions are 0. We can add them back if we apply decentralized linearized ADMM. So recall we have these constraints for every pair of edges ij. Now it couples these xi variables. To decouple them, to separate a set of variables, we introduce ye, where e stands for the edge ij. We introduce ye and let xi equal to ye and xj equal to ye. And this effectively equalizes xi and xj. So we obtain the equivalent formulation. But now with a new set of variables which decouple, when they're fixed, they decouple xi from xj. And then we can write down the Lagrangian. And in the Lagrangian, we have to introduce dual variables for these two constraints. For every edge, there are two constraints. The constraint with respect to I and constraint with respect to j, so we introduce two dual variables. And then we write down the augmented Lagrangian with augmentation parameter alpha. Because this has a ADMM form on X and on Y, in particular Y has no objective function, so we're going to have easy subproblems with Y, and we can also have relatively easy subproblems with every Fi of Xi, because every Xi is only related to Ye, where E are the edges that connect agent I to its neighbors. So we apply standard ADMM and obtain the three-step algorithm. Step 1 is update of Xi. If you look at the information, requires the dual variables, the Yij variables for all the edges I to j, where j are just the neighbors of the node I. And all the nodes, other than requiring these fixed numbers, fixed variables, can execute this update of xi independently. And then we're going to update ye for all the edges ij. Every ye's update requires information from the two ends of the edges. So here t equal to I and j. Then finally, we update the dual variable. There are going to be one dual variable for every edge, actually two dual variables for every edge. We do not have to implement this particular algorithm on a network because we can simplify them. The simplification can take some steps. First, observe there's missing a division size 1 over alpha. So we can substitute ye into the U update. And this is going to simplify the U update into this form. Now this form also, from this form we can observe that for every edge E, UIE one end and UIJ the other end, the sum of the two U variables is actually equal to 0 since the first iteration. So we can eliminate at least one of the U's. So we're gonna use Y, and also we're gonna plug this equation back into the YE update. So this is gonna simplify the YE update, and we're gonna keep one UIE. So we plug it in, we're gonna get this form. We slightly simplify the XI subproblem, but again, it's independent for all the nodes I. Then we look at one term in the update and define extra variable VIK as this average. And this is a neighborhood average. And then we also define this neighborhood average. And with these two additional variables, we are able to eliminate Y and U and keep X. And then we obtain the final algorithm, which is much shorter, and it's equivalent to the decentralized ADMM algorithm we described in 2 slides ago. In this algorithm, Xi are independently updated using information from Vi, and then the updated Xj's from the neighbors of node I is averaged to get a ik plus 1, and then node I can use its own Vj, Vi, Ai, as well as from the node I will use its own Vi and Ai, as well as updated Aik plus 1 to compute the updated Vi k plus 1. And this is called decentralized ADMM, and convergence follows from the standard convergence of ADMM. This method is indeed decentralized. Let's quickly describe how it is implemented. As I mentioned, Xi and Vi use only information that's stored at the node, so there's no communication needed. However, to update AI, you're gonna need the averaging the latest xi variables from your neighbors, and every node have to do it. So this is called neighbor reduction. So we have looked at decentralized ADMM. When the smooth function hi through hn are present, we can extend the method to decentralized linearized ADMM. And both decentralized ADMM and decentralized linearized ADMM methods are synchronous in the sense that if an agent is slow, then it can hold up its neighbors because its neighbors requires information to do their AI updates. And this can in turn hold up neighbors, and so on and so forth. So a single slow agent can hold up the progress of the entire network. Now, there's a solution. You can apply the asynchronous technique from chapter 6 and apply it to the ADMM methods we learned here. And that'll give us the asynchronous version of the decentralized methods. In the last part of this lecture, let's look at decentralized optimization with mixing matrices, which make decentralized algorithm more flexible. So let's first define the stack operator and use boldface letter to denote the stacked variables. We actually stack the transpose of these vectors. Although little x is actually a matrix, we still use a lowercase because when a mixing matrix is multiplied to the left of x, we emphasize the effect of this mixing on every component individually. So in fact, much of the analysis and the development in the last part is the same when p equals 1. When p is greater than 1, there's no different treatment. So similarly, we also stack the optimal vectors and create a matrix x star. So all the rows are equal one another. And given two stacked vectors x and y, their inner products are the inner products of the x and y at individual agents. And given a symmetric positive semi-definite matrix A, we can define the A-induced norm. In particular, the norm of this matrix is just the norm induced by identity matrix, which is the inner product of x and x, which decomposes to the 2 norm of xi squared of and take the sum over individual agents. To continue, let's define f of the stacked variable x, which is the separable sum of fi of xi. Similarly, hx is separable sum of hi of xi. The proximal of f of x is the stacked results of individual fi's proximal operator with input xi. Similarly, gradient hx is a stack of the individual hi's gradient at xi. We say the stacked variable is inconsensus if all the components x1 through xn are equal. A feasible point of model 3 is inconsensus, and some of the methods in this section produce iterates that are consensus in the limit. Now let's introduce mixing matrix. We use the letter W for mixing matrix. It roughly represents how neighborhood averaging is done in the network. And it's important to analyze the eigenvalues of matrix W. We say that W is a decentralized mixing matrix with respect to given graph if Wij is always equal for non-edge, and Wij, in other words, Wij can only be non-zero if I equal to j, so Wii can be non-zero, and if Wij is an edge. In other words, if two nodes ij are directly connected, there's a mixing coefficient Wij for them. Multiply W to Y can be evaluated in a decentralized manner because this sum the i's component is written as the sum of the individual components of wi to y. And this can be evaluated because j is a neighbor of I, and that's only when wij's are non-zero. So when j equal to I or is a neighbor, you take the sum. Let's look at some examples of W. Introduce the W matrix such that Wij is equal to the size of the number of neighbors of node I and 0 otherwise. So in this case, Wii is actually 0 and Wij for neighbor j equal to 1 over the number of neighbors. And introduce this function which average fi with the coefficient 1 over the neighbors. And then with this introduction, we can express the decentralized ADMM method we learned a few slides ago in the simple form, utilizing this defined function f tilde as well as the W matrix. So this particular line means that every AI is just the neighborhood average. Here we have a more important example, and in this example we're going to compute the average of vectors in a network. Suppose agent I has a vector xi, it's p-dimensional, and our goal is to compute their average. If agent I is a sensor, xi represents the sensor reading, we're computing the average of the readings over the network. This is a special optimization with fi of xi set to the least squares between x and xi. So the method we consider is this iteration where we keep multiplying w to vector xk to xk. This amounts to repeatedly doing neighborhood averaging. And the initial vector x0 is set to the input reading. And this iteration will converge to the actual mean or the stacked mean for any arbitrary x0 if and only if w times vector 1 is 1. Vector 1 transpose times w on the left is vector 1 transpose, and the largest eigenvalue of w is 1. Because of this, actually, w does have a eigenvalue equal to 1 because of that. And the rest of the eigenvalues, real or complex, will have a modulus strictly less than 1. And this statement is given in exercise 11.4. Roughly speaking, this condition implies that if you input a consensus vector, and then neighborhood averaging should return the same consensus vector. And this condition means that the total sum, the total mass is preserved by doing one iteration of this local averaging. And the eigenvalue condition implies the iteration converge because it'll maintain the eigenvector, maintain the vector along the vector 1 and shrink all the other eigenmodes. So that was a great example of a mixing matrix. So in this section, in the rest of this section, we're going to use a mixing matrix in optimization. And for that, we make the following assumptions. We assume W is symmetric. We assume the null space of identity minus W is the span of vector 1. And this means the only vector that multiplied by W equal to that vector is the vector 1 or its scalar multiple. And we assume that all the eigenvalues except the first eigenvalue is strictly less than 1. And because of this assumption, symmetry assumption, all these eigenvalues are actually real. 4a was not assumed in decentralized ADMM averaging, but this is the very common assumption, and it makes analysis easier. 4b implies x is inconsensus if and only if x equal to wx. And this is required almost by all decentralized optimization methods. and we have mentioned for C. Let's look at mixing matrices that satisfy the assumptions. The first example is Laplacian-based mixing matrix. Let L, matrix L, denote the so-called graph Laplacian, where Lij is the size of the neighborhood if I equal to j, and -1 for when I and j are neighbors. Otherwise, for those non-connected nodes, Lij is 0. And the mixing matrix identity minus 1 over tau of this L. And tau is just any constant satisfying tau greater than half of the maximum eigenvalue of L. And this ensures that W is symmetry by this construction, and W satisfies this also by this construction, and by the choice of tau, or the rest of the eigenvalue of W is strictly less than 1. Another common mixing matrix is the Metropolis mixing matrix. For any edge ij in the network, Wij is set up to 1 over the maximum of i's neighbor size and the j's neighbor size plus little epsilon. And Wii is chosen such that the row sum is 0. The row sum is 1. And for all the other, as usual, for all the other edges, the Wij is 0. Then this W satisfies the symmetry assumption, the sum of row equal to 1 assumption, and this eigenvalue assumption. A mixing matrix is very closely related to stochastic matrix, but they have some differences. A P matrix, a square matrix P is a stochastic matrix if all the entries are non-zero and the sum of every row is equal to 1. So the difference is a mixing matrix may have negative entries. Another difference is how they are used. With a stochastic matrix satisfying this, it basically means in a Markov chain setting, the transition preserves the total mass. And often the transition is right multiplied. So pi k presents the distribution of how likely the distribution of time you're in certain states. And right multiplied p give you the transition probability of how much time you're in each state. However, the mixing matrix is often right multiplied by the stacked vector in a decentralized optimization method. When a mixing matrix is a stochastic matrix, i.e. all the entries are non-negative, one can utilize the classic Markov chain theory based on Perron-Frobenius theorem. For example, we're going to have, for an irreducible Markov chain, we're going to have this property automatically hold. And if the Markov chain is also aperiodic, then the eigenvalue property will also hold. And we describe the definition of a irreducible and aperiodic Markov chain as follows. So now let's use a mixing matrix to derive some decentralized methods. The first two methods we derive are inexact methods. So we consider this setup where there's no proximable functions. There are only the sum of hi of xi's, only the smooth functions. Consider W satisfying the three properties. We can rewrite problem 1 equivalently in this form because of the span constraint. So the only x satisfy this constraint is a consensus on x. So we consider inexact decentralized method DGD and diffusion, which are two methods. They will solve the equation, solve this problem 5 to a proximate solution. One of the earliest decentralized optimization method is decentralized gradient descent. It can be obtained from this penalty formulation, where instead of enforcing identity minus W times x equals 0, we penalize the violation. If x is in consensus, then this term is 0. If X is not in consensus, this term is positive. This term penalizes the level of inconsistency among the xi's. For alpha small, this penalty parameter is large, so we expect at the solution, the consensus constraint is at least approximately satisfied. So this formulation will approximate problem 5. Because both terms are differentiable, we can apply gradient descent, and we use step size alpha to cancel 1 over alpha. And then after combination, we can obtain this very nice formulation where the first term is neighborhood averaging or neighborhood weighted averaging using mixing matrix W, and the second term is just individual gradients of hi of xi, and this term is computed individually by all the agents. Because both terms are decentralized, this is a decentralized method, which is called decentralized gradient descent. And because this term you combine from the neighbors, and this term called adapt, which try to adapt to individuals' objective, and this method is also called combine then adapt method. And using standard analysis, applying standard analysis to this this method, we obtain if the problem has a solution, HIs are LH smooth and step size is less than this number, then XK converges to a solution of the penalty formulation, which again is only approximation to problem 5. The diffusion is a method that's similar to decentralized gradient descent but has important differences. We make an additional assumption on mixing matrix W and assume it's strictly positive definite, which allows W inverse to also be strictly positive definite. Now this assumption together with eigenvalue assumptions, we're going to have all the eigenvalues of W is greater than or equal to 1, because identity has eigenvalues exactly equal to 1, so this matrix is positive semi-definite with the inverse, okay, with the difference. This is a positive semi-definite matrix, which qualifies as qualifies to induce a norm. It turns out this norm also penalizes the inconsistencies among these xi's. And when we can apply variable metric gradient descent from chapter 2, section 8, with this matrix, one to cancel W and the other to cancel alpha, with this matrix as the metric. And in variable metric gradient descent, it's actually the inverse of the metric that is used here. And then this part is the gradient of the objective function. This is the variable metric. This is from variable metric, and after simplification, we get this new formulation where we first adapt to local objective and then combine. Therefore, this method is called adapt then combine method, and it is also called diffusion method. Applying analysis of variable metric gradient descent, we can obtain that if the penalty formulation has a solution, H are LH smooth, and step size now can be taken from a larger range, that is 2 over LH, then XK converges to a solution of the penalty formulation, not the formulation 5. Let's compare the two methods, DGD and diffusion. So DGD has the advantage of allowing a larger step size, which often translates to faster convergence. DGD, however, does not require the additional assumption that W being positive definite, and allows Wx, which is weighted averaging, and alpha times grad H, which is individual agents computation of gradients, to be executed simultaneously. So every step, it's possible to implement a step of DGD faster than a step of diffusion. So one has fewer iterations, the other has a faster step. When W does not satisfy the assumption of diffusion, you can still use diffusion by using this matrix instead of W. Now this matrix is averaging between identity and W, with weight theta, it bumps up the smallest eigenvalue of W. Specifically, theta can be taken from this range. Because the minimal eigenvalue of a symmetric W under assumption is always greater than -1, and theta equal to 1/2, there's division sign, and always works. Recently, there are faster methods, and they are called exact decentralized methods, and they can use a mixing matrix. Since identity minus W is symmetric in the part of semi-definite, there exists a symmetric matrix U such that U squared equal to half of 1 minus W. We do not need to come up with U because U only exists in the derivation analysis, and the actual methods we will derive will use W instead. But because of this property, the null space of U is still the span of 1, which is the same span of identity minus W. So using this property, we can express the consensus constraint in Ux equals 0 in the simple form. And we're going to come up with this equation 6, formulation 6, where we're going to minimize the sum of the separable objective fi of x and sum of separable objective hi of xi. Two methods we're going to present is called PG extra and NIDS of NIDS. They converge to exact solution of the problem 6. To present PG extra, let's look at an exercise of chapter 3. This is the second version of a Candet-Wu prime module splitting. So using notation back in chapter 3, we're looking at minimizing sum of f, a CCP and the proximable function, and h of x, which is a CCP smooth function, and a CCP proximable function g of matrix A times x. In the derivation of Candet-Wu, instead of using the metric in the chapter, we use new metric. And this metric has a different sign. The metric in the chapter will have negative signs here. Here we don't have the negative sign. And using a slightly different metric, we're going to get a method, the second version of Candet-Wu's method. And in the second version, we're going to first update U, then update X. In the U update, it's pretty simple. In the X update, they're going to be 2UK plus 1, the latest the U minus UK. In the first version that presented in the chapter, in chapter 3, U and X are almost reversed. X is first updated, and U is then updated with a 2xk plus 1 minus xk inside of the input to their procs. So to derive PG extra, we're going to need this version. And the convergence result is, assuming total duality holds, both alpha and beta strictly positive, and this inequality is satisfied, which limits alpha and alpha beta, and H, where H is an L smooth, then both the primal and dual solution will converge to a saddle point. Recall in the problem 6, we have a constraint. A constraint is an indicator, essentially an indicator function. And the constraint has a matrix U. Matrix U is symmetric, so we let both A and A transpose in the last slide be just matrix U, and let the indicator function be function G in the last slide. And directly applying the method in the last slide give us this iteration. So this special case of second version of Candet-Wu. And we can simplify this method by first letting beta equal to alpha, inverse of alpha, and to eliminate U, replace U by W, we introduce a little wk as 1 over beta U times uk. And this effectively multiply a U matrix in the first equation, creating U squared, which gives us half of 1 minus W. This helps us obtain a simpler form. So after this simplification, we obtain xk plus 1 as the combination, adaptation, correction with this dual variable wk, and taking the procs, and then update the wk variable using the combination of xk. So we can initialize x0 arbitrarily and initialize w0 to 0, which avoids computing u matrix u times little u0. And this method is called pgextra. And pgextra is decentralized because this calculation is decentralized. This is local. wk is a stacked vector, and every vector little wi is stored at agent I. And this proc is also local. And during the update of w, this has already been computed above, and everything else is local. So this is a decentralized method. When total duality holds, then alpha satisfies this step size condition, which is derived from the last slide using this property, using the eigenvalue property of u squared, and assuming all the h are L-smooth, then we have xk converge to a solution of 6, or problem 5. Before we introduce NIDS, we have to review the PD3O, prime module 3 operator splitting method. Once again, we look at the formulation from chapter 3. So PD3O from chapter 3 is the method of this form. In this form, we first update x using variable uk and the gradient of h, and then update the dual variable uk plus 1 in this form. So recall PD3O was obtained by applying a dys for fixed point iteration to a formulation obtained from the BCV technique. When total duality holds, alpha beta positive, alpha beta satisfy the step size condition alpha less than 2 over L, where L is the smoothness constant of grad A of H. And then this correction, this W xk iteration will converge to a solution. Applying PD3O to this formulation 6, which is a little rewritten using the indicator function, we're going to get this iteration. We first update the x and then update u. But this still uses matrix U. We need a simple transform to use the mixing matrix W. So to eliminate U and get W, introduce this vector. And to simplify, use beta equal to 1 over alpha, we can get this simplified form. So x will be a prox of zk. If zk is a stacked vector and every zi is stored locally at agent I, prox alpha f is local computation, decomposes to local computation, so this step is local. The update of z will use the gradient of h at xk, and which can be computed locally, and require w times xk and w times xk plus 1. Of course, we're going to calculate w xk and store it locally. And this involves local communication, neighborhood communication, which is decentralized. So both x and z can be updated in the decentralized fashion. Initialization is arbitrary for x0, but not so for z0. We have to use this formulation. We can cheat by using u0, by setting u0 to 0, so therefore skip this term, and we only need z0 equal to x0 minus alpha times grad h x0. And this method is called NIDS, short for Network Independent Step Size method. And this is because alpha only depends on 2 over LH, is independent of the network's eigenvalue, is independent of the eigenvalues of W, therefore independent of the network topology. Every agent in the network can choose alpha independently, use its own HI, it's in the exercise. Let's compare pgextra and NIDS. So pgextra depends on eigenvalues of W, which indirectly depends on the network topology. This makes the choice of alpha more difficult when the network is not fully known, or the network in some cases dynamic, changes over time. In contrast, NIDS does not need that information, and the choice of alpha is actually larger if you compare the two formulation. And on the other hand, PGExtra by the formulation allows you to simultaneously do the neighborhood averaging and the local gradient computation, which can save time of each iteration. However, an IDS requires you to do W after you get the local computation down. The formulations of both methods have two lines. However, we can simplify them by setting the CCP proximal function f to 0 and introduce this W total for shorter notation. So PGExtra will have this form, and an IDS will have similar form except the W total is applied to the sum rather than in PGExtra where W total is immediately applied before the gradient is applied. So PGExtra resembles decentralized gradient descent, while an IDS resembles diffusion. And they have also similar advantages and disadvantages. It's time to conclude this chapter. Distributed optimization can take advantage of the problem structure, mainly the summable structure, so we can solve extremely large instances using multiple agents and running multiple agents at the same time. When there is a central coordinator which collects and distributes data, the method can rely on aggregating either distributed gradient or averaging the iterates stored locally through a reduce operation. However, when there's no central coordinator, the problem, the communication bottleneck can be reduced. It uses neighborhood communication instead. Decentralized methods are more difficult to obtain over distributed optimization methods. Often standard distributed optimization method with a central controller can be directly obtained through, say, gradient descent or forward-backward splitting. However, decentralized optimization method, especially the exact version of decentralized optimization method, requires primal dual splitting applied in a skillful manner, and often some simplification using change of variables. This concludes this chapter.